Welcome friends. In this chapter, we define and learn linear congruence and number theoretical function Euler phi function. Definition. A linear congruence is an equation of the form Ax congruent to B mod n. A solution of a linear congruence is an integer x0 for which Ax0 congruent to B mod n. Remark. Ax0 congruent to B mod n if and only if n divides Ax0 minus b. That is, if and only if Ax0 minus b is equal to n y0 for some integer y0. Hence, the problem of finding all integers that will satisfy the linear congruence Ax congruent to B mod n is identical with that of obtaining all solution of the linear Diophantine equation Ax minus ny is equal to b. It is convenient to treat two solutions of Ax congruent to B mod n that are congruent modulo n as being equal even though they are not equal in the usual sense. For instance, x is equal to minus 9 and x is equal to 3 both satisfy the congruence 3x congruent to 9 mod 12 because 3 congruent to minus 9 mod 12. Hence, x is equal to minus 9 and x is equal to 3 are not counted as different solutions. When we refer to the number of solutions of Ax congruent to B mod n, we mean the number of incongruent integers satisfying this congruence. Theorem 1. The linear congruence Ax congruent to B mod n has a solution if and only if D divides B, where D is equal to GCD of an. If D divides B, then it has D mutually congruent solutions modulo n. Proof. In the remark above, we have observed that the given congruence is equivalent to the linear Diophantine equation Ax minus ny is equal to b. We know that the latter equation can be solved if and only if D divides B, where D is equal to GCD of an. Moreover, if it is solvable and x0, y0 is one specific solution, then any other solution has the form x is equal to x0 plus n by dt, y is equal to y0 plus a by dt for some choices of t. Among the various integers satisfying the first of these formulas, consider those that occur when t takes on the successive values t is equal to 0, 1, 2, etc. d minus 1, x0, x0 plus n by d, x0 plus 2n by d, etc. x0 plus d minus 1 into n by d. We claim that these integers are incongruent modulo n and all other such integers x are congruent to some one of them. If it happen that x0 plus n by d t1 congruent to x0 plus n by d t2 mod n, where 0 less than or equal to t1 less than t2 less than or equal to d minus 1, then we would have n by d t1 congruent to n by d t2 mod n. Now, GCD of n by d n is equal to n by d. The factor n by d could be cancelled to arrive at the congruence t1 congruent to t2 mod d, which is to say that d divides t2 minus t1. But this is impossible in view of the inequality 0 less than t2 minus t1 less than d. It remains to argue that any other solution x0 plus n by d t is congruent modulo n to one of the d integers listed above. The division algorithm permits us to write t as t is equal to qd plus r, where 0 less than or equal to r less than or equal to d minus 1. Hence, x0 plus n by d t is equal to x0 plus n by d qd plus r, which is equal to x0 plus nq plus n by d r, which is congruent to x0 plus n by d r mod n, with x0 plus n by d r being one of our d selected solutions. This completes the proof. The following result is a special case of the theorem when a and n are assumed to be relatively prime. Corollary. If GCD of an is equal to 1, then the linear congruence Ax congruent to 1 mod n has a unique solution called the multiplicative inverse of A modulo n. Example 1. Consider the linear congruence 18x congruent to 30 mod 42. Because GCD of 18, 42 is equal to 6 and 6 surely divides 30, theorem guarantees the existence of exactly 6 solutions which are incongruent modulo 42. By inspection, one solution is found to be x is equal to 4. Our analysis tells us that the 6 solutions are as follows. X is equal to 4 plus 42 by 6t, which is congruent to 4 plus 7t mod 42, t is equal to 0, 1, etc. 5. That is, x congruent to 4, 11, 18, 25, 32, 39 mod 42. Example 2. Solve the linear congruence 9x congruent to 21 mod 42. Solution. As GCD of 9, 30 is equal to 3 and 3 divides 21, we know that there must be 3 incongruent solutions. One way to find these solutions is to divide the given congruence through by 3, thereby replacing it by the equivalent congruence 3x congruent to 7 mod 10. The relative primenesses of 3 and 10 implies that the later congruence admits a unique solution modulo 10. Although it is not the most efficient method, we would test the integers 0, 1, 2, etc. 9 in turn until the solution is obtained. A better way is this. Multiply both sides of the congruence 3x congruent to 7 mod 10 by 7 to get 21x congruent to 49 mod 10, which reduces to x congruent to 9 mod 10. This simplification is no accident, for the multiples 0 into 3, 1 into 3, 2 into 3, etc. 9 into 3 form a complete set of residues modulo 10. Hence, one of them is necessarily congruent to 1 modulo 10. But the original congruence was given modulo 30. So that its incongruent solutions are sought among the integers 0, 1, 2, etc. 29, taking t is equal to 0, 1, 2 in the formula x is equal to 9 plus 10t. We obtain 9, 19, 29 and hence x congruent to 9 mod 30, x congruent to 19 mod 30, x congruent to 29 mod 30 are the required 3 solutions of 9x congruent to 21 mod 30. A different approach to the problem is to use the method that is suggested in the proof of theorem 1. Because the congruence 9x congruent to 21 mod 30 is equivalent to the linear Diophantine equation 9x minus 30y is equal to 21. We begin by expressing 3 is equal to GCD of 9, 30 as a linear combination of 9 and 30. It is found either by inspection or by using the Euclidean algorithm that 3 is equal to GCD of 9, 30. So that 21 is equal to 7 into 3, which is equal to 9 into minus 21 minus 30 into minus 7. Thus, x is equal to minus 21, y is equal to minus 7 satisfy the Diophantine equation, and in consequence all solutions of the congruence in question are to be found from the formula x is equal to minus 21 plus 30 by 3 into t, which is equal to minus 21 plus 10t. The integers x is equal to minus 21 plus 10t where t is equal to 0, 1, 2 are incongruent modulo 30, but all are congruent modulo 10. Thus, we end up with the incongruent solutions x congruent to minus 21 mod 30, x congruent to minus 11 mod 30 and x congruent to minus 1 mod 30. The corresponding positive numbers are x congruent to 9 mod 30, x congruent to 19 mod 30 and x congruent to 29 mod 30. System of linear congruence. We now turn to the problem of solving a system of simultaneous linear congruence. A1x congruent to B1 mod M1, A2x congruent to B2 mod M2, etc. ARX congruent to BR mod MR. We shall assume that the moduli Mk are relatively prime in pairs. Evidently, the system will admit no solution unless each individual congruence is solvable. That is, unless dk divides bk for each k, where dk is equal to GCD of ak mk. When these conditions are satisfied, the factor dk can be cancelled in the kth congruence to produce a new system having the same set of solutions as the original one. A1 dash x congruent to B1 dash mod n1, A2 dash x congruent to B2 dash mod n2, etc. AR dash congruent to BR dash mod nr, where nk is equal to mk by dk and GCD of ni nj is equal to 1 for I not equal to j. In addition, GCD of ai dash ni is equal to 1. The solution of the individual congruence assumes the form x congruent to C1 mod n1, x congruent to C2 mod n2, etc. x congruent to CR mod nr. Thus, the problem is reduced to one of finding a simultaneous solution of a system of congruence of this simpler type. Theorem 2, Chinese remainder theorem. Let n1, n2, etc. nr be positive integers such that GCD of ni nj is equal to 1 for I not equal to j. Then the system of linear congruence x congruent to A1 mod n1, x congruent to A2 mod n2, etc. x congruent to AR mod nr has a simultaneous solution which is unique modulo the integer n1, n2, etc. nr. Proof. We start by forming the product n is equal to n1 into n2 into etc. into nr. For each k is equal to 1, 2, etc. r, let nk is equal to n by nk, which is equal to n1 into etc. into nk minus 1 into nk plus 1 etc. nr. That is, nk is the product of all the integers ni with the factor nk omitted. By hypothesis, the ni are relatively prime in pairs, so that GCD of nk is equal to 1. According to the theory of a single linear congruence, it is therefore possible to solve the congruence nkx congruent to 1 mod nk. Call the unique solution xk. Claim the integer x bar is equal to a1 n1 x1 plus a2 n2 x2 plus etc. plus ar nr xr. Equation number 1 is a simultaneous solution of the given system. First, observe that ni congruent to 0 mod nk for I not equal to k because nk divides ni. In this case, the result is x bar is equal to a1 n1 x1 plus etc. plus ar nr xr congruent to ak nk xk mod nk. But the integer xk was chosen to satisfy the congruence nkx congruent to 1 mod nk, which forces x bar congruent to ak into 1, which is congruent to ak mod nk. That is, the integer x bar is equal to a1 n1 x1 plus a2 n2 x2 plus etc. plus ar nr xr is a simultaneous solution of the given system. This shows that a solution to the given system of congruence exists. As for the uniqueness assertion, suppose that x dash is any other integer that satisfies these congruences. Then x bar congruent to ak congruent to x dash mod nk, k is equal to 1, 2, etc. r. And so nk divides x bar minus x dash for each value of k. That is, n1 divides x bar minus x dash, n2 divides x bar minus x dash, etc. nr divides x bar minus x dash. With a GCD of ni nj is equal to 1 for I j is equal to 1, 2, etc. r with I not equal to j. This with the application of mathematical induction on the result, if A divides C and B divides C with a GCD of AB is equal to 1, then AB divides C gives n1 into n2 etc. into nr divides x bar minus x dash. Hence, x bar congruent to x dash mod n. This completes the proof of the Chinese remainder theorem. Example 3. Find the least positive integer x such that x congruent to 5 mod 7 and x congruent to 3 mod 13. Solution. In the notation of Chinese remainder theorem, we have n is equal to 7 into 11 into 13, which is equal to 1001, and n1 is equal to n by 7, which is equal to 143, n2 is equal to n by 11, which is equal to 91, n3 is equal to n by 13, which is equal to 77. Now, the linear congruence 143x congruent to 1 mod 7, 91x congruent to 1 mod 11, 77x congruent to 1 mod 13 are satisfied by x1 is equal to 5, x2 is equal to 4, x3 is equal to 12 respectively. Thus, a solution of the system is given by x is equal to 5 into 143 into 5 plus 7 into 91 into 4 plus 3 into 77 into 12, which is equal to 8895, modulo 7 into 11 into 13, which is equal to 1001. We get the unique solution x is equal to 8891 congruent to 887 mod 1001. Thus, 887 is the least positive solution. Example 4. The problem posed by Sansu is the following. Find a number that leaves the remainders 2, 3 and 2 when divided by 3, 5 and 7 respectively. Solution. The given problem corresponds to the system of three congruences x congruent to 2 mod 3, x congruent to 3 mod 5, x congruent to 2 mod 7. In the notation of Chinese remainder theorem, we have n is equal to 3 into 5 into 7, which is equal to 105. And n1 is equal to n by 3, which is equal to 35, n2 is equal to n by 5 is equal to 21, n3 is equal to n by 7 is equal to 15. Now, the linear congruence 35x congruent to 1 mod 3, 21x congruent to 1 mod 5, 15x congruent to 1 mod 7 are satisfied by x1 is equal to 2, x2 is equal to 1, x3 is equal to 1 respectively. Thus, a solution of the system is given by x is equal to 2 into 35 into 2 plus 3 into 21 into 1 plus 2 into 15 into 1, which is equal to 233 modulo 105. We get the unique solution x is equal to 233 congruent to 23 mod 105. Example 5. Show that there is no x for which both x congruent to 29 mod 52 and x congruent to 19 mod 72. Solution. Since 52 is equal to 4 into 13, the first congruence is equal to the simultaneous congruence x congruent to 29 mod 4 and x congruent to 29 mod 13, which reduces to x congruent to 1 mod 4 and x congruent to 3 mod 13. Similarly, 72 is equal to 8 into 9, and the second congruence given in equivalent to the simultaneous congruence x congruent to 19 mod 8 and x congruent to 19 mod 9. This reduces to x congruent to 3 mod 8 and x congruent to 1 mod 9. The given congruences are inconsistent because there is no x for which both x congruent to 1 mod 4 and x congruent to 3 mod 8. Hence, there is no x for which both x congruent to 29 mod 52 and x congruent to 19 mod 72. Example 6. Determine whether the system x congruent to 3 mod 10, x congruent to 8 mod 15, x congruent to 5 mod 84 has a solution, and find them all if any exist. Solution. We factor each modulus into prime powers. Since 10 is equal to 2 into 5, the first congruence of the system is equivalent to the two simultaneous congruences x congruent to 3 mod 2 and x congruent to 3 mod 5. Similarly, the second congruence of the system is equivalent to two conditions x congruent to 8 mod 3 and x congruent to 8 mod 5, while the third congruence is equal to the three congruents x congruent to 5 mod 4, x congruent to 5 mod 3 and x congruent to 5 mod 7. The new system of 7 simultaneous congruents is equivalent to the ones given, but now all moduli are prime powers. We consider the powers of 2 first. The two conditions are x congruent to 3 mod 2 and x congruent to 1 mod 4. These two are consistent, but the second one implies the first, so that the first one may be dropped. The conditions modulo 3 are x congruent to 8 mod 3 and x congruent to 5 mod 3. These are equivalent and may be expressed as x congruent to 2 mod 3. Third, the conditions modulo 5 are x congruent to 3 mod 5 and x congruent to 8 mod 5. These are equivalent. So, we drop the second of them. Finally, we have the condition x congruent to 5 mod 7. Hence, our system of 7 congruents is equivalent to the 4 conditions x congruent to 1 mod 4, x congruent to 2 mod 3, x congruent to 3 mod 5 and x congruent to 5 mod 7. Hence, the moduli are relatively prime in pairs. So, we may apply the formula used in the proof of the Chinese remainder theorem. Proceeding as in the solution of example 3, we find that x satisfies the given congruence if and only if x congruent to 173 mod 420. Example 7. Solve the linear congruence 17x congruent to 9 mod 276. Solution. Because 276 is equal to 3 into 4 into 23. This is equivalent to finding a solution for the system of congruence 17x congruent to 9 mod 3, 17x congruent to 9 mod 4, 17x congruent to 9 mod 23, or x congruent to 0 mod 3, x congruent to 1 mod 4, 17x congruent to 9 mod 23. Note that if x congruent to 0 mod 3, then x is equal to 3k for any integer k. We substitute into the second congruence of the system and obtain 3k congruent to 1 mod 4. Multiplication of both sides of these congruents by 3 gives us k congruent to 9k congruent to 3 mod 4. Hence, k is equal to 3 plus 4j, where j is an integer. Then, x is equal to 3 into 3 plus 4j, which is equal to 9 plus 12j. For x to satisfy the last congruence, we must have 17 into 9 plus 12j congruent to 9 mod 23 or 204j congruent to minus 144 mod 23, which reduces to 3j congruent to 6 mod 23. Hence, j is equal to 2 mod 23. This yields j congruent to 2 plus 23t with t an integer, and hence x is equal to 9 plus 12 into 2 plus 23t, which is equal to 33 plus 276t. Theorem 3. The system of linear congruents ax plus by congruent to r mod n, cx plus dy congruent to s mod n has a unique solution modulo n whenever GCD of AD minus BC n is equal to 1. Proof. Let us multiply the first congruence of the system by D, the second congruence by B, and subtract the lowest result from the upper. These calculations yield AD minus BC into x congruent to dr minus bs mod n, equation number 1. The assumption GCD of AD minus BC comma n is equal to 1 ensures that the congruence AD minus BC into Z congruent to 1 mod n possess a unique solution. Denote the solution by T. Then AD minus BC into T congruent to 1 mod n, equation number 2. When congruence 1 is multiplied by T, we obtain AD minus BC into T congruent to T into dr minus bs mod n. Using 1, we obtain x congruent to T into dr minus bs mod n. A value for y is found by a similar elimination process. Multiply the first congruence of the system by C, the second one by A, and subtract to end up with AD minus BC into y congruent to AS minus CR mod n, equation number 3. Multiplication of these congruents by T leads to y congruent to T into AS minus CR mod n. A solution of the system is now established. Example 8. Illustration of Theorem 3. Solve the system 7x plus 3y congruent to 10 mod 16, 2x plus 5y congruent to 9 mod 16. Solution. Because GCD of 7 into 5 minus 2 into 3 comma 16 is equal to GCD of 29 comma 16, which is equal to 1. By Theorem 3, a solution exists. It is obtained by the method developed in the proof of the above theorem. Multiplying the first congruence by 5, the second one by 3 and subtracting, we arrive at 29x congruent to 5 into 10 minus 3 into 9, which is congruent to 23 mod 16. The above is the same as 13x congruent to 7 mod 16. Multiplication of this congruence by 5, noting that 5 into 13 is congruent to 1 mod 16, produces x congruent to 35 congruent to 3 mod 16. When the variable x is eliminated from the system of congruence in a like manner, it is found that 29y congruent to 7 into 9 minus 2 into 10 congruent to 43 mod 16. But then 13y congruent to 11 mod 16, which upon multiplication by 5 results in y congruent to 55 congruent to 7 mod 16. The unique solution of our system turns out to be x congruent to 3 mod 16, y congruent to 7 mod 16. Euler's phi function. Definition. For n greater than or equal to 1, let phi of n denote the number of positive integers not exceeding n that are relatively prime to n. Example 9. Phi of 30 is equal to 8. For among the positive integers that do not exceed 30, there are 8 that are relatively prime to 30. Specifically 1, 7, 11, 13, 17, 19, 23, 29. Example 10. Phi of 1 is equal to 1, phi of 2 is equal to 1, phi of 3 is equal to 2, phi of 4 is equal to 2, phi of 5 is equal to 4 and so on. Notice that phi of 1 is equal to 1 because GCD of 1 comma 1 is equal to 1. In the event n greater than 1, then GCD of n comma n is equal to n not equal to 1, so that phi of n can be characterized by the following definition. Definition. Phi of n is the number of integers less than n and relatively prime to it. The function phi is called Euler phi function. Result. Phi of n is equal to n minus 1 if and only if n is prime. Proof. If n is a prime number, then every integer less than n is relatively prime to it. Hence, phi of n is equal to n minus 1. Conversely, if n greater than 1 is composite, then n has a divisor d such that 1 less than d less than n. It follows that there are at least 2 integers among 1, 2, 3, etc. n that are not relatively prime to n, namely d and n itself. As a result, phi of n less than or equal to n minus 2, that is phi of n not equal to n minus 1. Hence, considering contrapositive, we have phi of n is equal to n minus 1 implies n is prime. This completes the proof. Example 11. Show that the sum of all the integers which are less than n and prime to it is 1 by 2 n phi of n. Solution. If x is any integer less than n and prime to it, then n minus x is also an integer less than n and prime to it. Denote the integers by 1, p, q, r, etc. and their sum by s. Then s is equal to 1 plus p plus q plus r plus etc. plus n minus r plus n minus q plus n minus p plus n minus 1. The sum consisting of phi of n terms. Writing the series in the reverse order, we obtain s is equal to n minus 1 plus n minus p plus n minus q plus n minus r plus etc. plus r plus q plus p plus 1. Hence, by addition, 2s is equal to n plus n plus n plus etc. to phi of n terms, and therefore 2s is equal to n into phi of n, and so s is equal to 1 by 2 n phi of n. Theorem 4. If p is a prime and k greater than 0, then phi of p raised to k is equal to p raised to k minus p raised to k minus 1, which is equal to p raised to k into 1 minus 1 by p. Proof. Clearly, GCD of n p raised to k is equal to 1 if and only if p does not divide n. There are p raised to k minus 1 integers between 1 and p raised to k divisible by p, namely p, 2p, 3p, etc. p raised to k minus 1 p. Thus, the set 1, 2, etc. p raised to k contains exactly p raised to k minus p raised to k minus 1 integers that are relatively prime to p raised to k. And so, by the definition of the phi function, phi of p raised to k is equal to p raised to k minus p raised to k minus 1. Example 12. Illustration of theorem 4. Phi of 9 is equal to phi of 3 square, which is equal to 3 square minus 3, which is equal to 6. Phi of 16 is equal to phi of 2 raised to 4, which is equal to 2 raised to 4 minus 2 cube, which is equal to 16 minus 8 is equal to 8. Lemma. Given integers a, b, c, GCD of a, b, c is equal to 1 if and only if GCD of AB is equal to 1 and GCD of AC is equal to 1. Proof. First, suppose that GCD of A, BC is equal to 1 and put D is equal to GCD of AB. Then D divides A and D divides B, and hence D divides A and D divides BC. This implies that GCD of A, BC greater than or equal to D, which forces D is equal to 1. Similar reasoning leads to the statement GCD of AC is equal to 1. For the other direction, take GCD of AB is equal to 1, which is equal to GCD of AC, and assume that GCD of ABC is equal to D1 greater than 1. Then D1 must have a prime divisor P, because D1 divides BC, it follows that P divides BC. Consequence, P divides B or P divides C. If P divides B, then by virtue of the fact that P divides A, we have GCD of AB greater than or equal to P. Contradiction. In the same way, the condition P divides C leads to the equally false conclusion that GCD of AC greater than or equal to P. Thus, D1 is equal to 1 and the lemma is proven. Theorem 5. The function phi is a multiplicative function. Proof. It is required to show that phi of mn is equal to phi of m into phi of n whenever m and n have no common factor. Because phi of 1 is equal to 1, the result obviously holds if either m or n equals 1. Thus, we may assume that m greater than 1 and n greater than 1. Arrange the integers from 1 to mn in m columns of n integers each as follows. We know that phi of mn is equal to the number of entries in this array that are relatively prime to mn. By virtue of the lemma, this is same as the number of integers that are relatively prime to both m and n. The procedure of proof is this. Because GCD of Qm plus R, m, GCD of Rm, the numbers in the rth column are relatively prime to m if and only if R itself is relatively prime to m. Therefore, only phi of m columns contain integers relatively prime to m, and every entry in the column will be relatively prime to m. The problem is one of showing that in each of these phi of m columns, there are exactly phi of n integers that are relatively prime to n. For then, altogether there would be phi of m into phi of n numbers in the table that are relatively prime to both m and n. Now, the entries in the rth column, where it is assumed that GCD of Rm is equal to 1 R, m plus R, 2m plus R, etc. n minus 1 m plus R. There are n integers in this sequence and no two are congruent modulo n. Indeed, if km plus r congruent to jm plus r mod n with 0 less than or equal to k less than j less than n, it would follow that km congruent to jm mod n. Because GCD of mn is equal to 1, we could cancel m from both sides of this congruence to arrive at the contradiction that k congruent to j mod n. Thus, the numbers in the rth column are congruent modulo n to 0, 1, 2, etc. n minus 1 in some order. But if s congruent to t mod n, then GCD of Sn is equal to 1 if and only if GCD of Tn is equal to 1. The implication is that the rth column contains as many integers that are relatively prime to n as does the set 0, 1, 2, etc. n minus 1, namely phi of n integers. Therefore, the total number of entries in the array that are relatively prime to both m and n is phi of m into phi of n. This completes the proof of the theorem. Now it's a time to conclude. In this unit, first we discussed linear congruence followed by the Chinese remainder theorem, which is a method for finding solution of a system of linear equations. Next, we discussed an important number theoretical function, Euler phi function, with theorems and supporting examples. Before moving to the next session, let us try to answer these questions. Solve the following linear congruence. 25x congruent to 15 mod 29, 5x congruent to 2 mod 26, 6x congruent to 15 mod 21. Calculate phi of 1001, phi of 5040 and phi of 36,000. Find the solutions of each of the following system of congruence. A. 5x plus 3y congruent to 1 mod 7, 3x plus 2y congruent to 4 mod 7. B. 7x plus 3y congruent to 6 mod 11, 4x plus 2y congruent to 9 mod 11. Hope you enjoyed this session. See you next time. Till then, take care.